We move next to section 342, and we'll be talking about the derivative of a to the x. So we just finished finding the derivative of e to the x, and we're going to wonder now, what if that base were something other than the number e? So what about it? What if we had an exponential function that was a base that was not e? Say, for instance, 2 to the x, or 5 to the x, or 1/2 to the x. How would we differentiate a function such as that? Well, first up, we're going to assume that that base is both positive and not 1, since negative numbers raised to arbitrary real powers are not always real numbers, and y equals 1 to the x is a constant function. So we want a positive value for the base that is not 1. And then what we'll do is lean on the idea that we know that the derivative of e to the u is e to the u du dx, and rewrite a to the x in terms of e using properties of logarithms. So let's begin there. Let's rewrite the base a as e to the power of natural log of a. And if you recall from your logarithm properties, this is true because we say that e and natural log are inverse functions. What is done by one is undone by the other when they are composed, and this would come out essentially as just a. So here we go. We want to find the derivative with respect to x of a to the x. In our next step, we're going to rewrite a to the x in terms of e. So we write that as e to the power of the natural log of a to the power of x. Well, then we're going to take advantage of the rules of logarithms and take this exponent x back out in front as a scalar multiplier to the natural log of a. So this is now the derivative of e to the power of x times the natural log of a. And so we're written in terms of e to the u power, and we can differentiate this. So we know that the derivative of e to the u power is itself first, so e to the x times natural log of a times the derivative of x to the x times natural log of a. So I'm going to take a step and write that in as d dx of x times natural log of a. So what is the derivative of that? Well, since a is a constant, taking the natural log of a is also a constant. So x times a constant, that derivative is just the constant. So this derivative of d dx x natural log a is just natural log a. So we can write this now as e to the power of x times natural log of a times the natural log of a. So what does this mean when we simplify? Well, let's substitute back in place what we said this e to the x natural log of a originally was. Well, e to the x natural log of a was actually this first, e to the natural log of a to the x, and before that, it was just a to the x. So this I can replace with a to the x times a natural log of a. And there we have it. The derivative with respect to x of the base a to the power of x function is itself a to the x times the natural log of a. So almost the same as the e to the x function, except we have this extra factor of times natural log of that base. So here it is more formally. The derivative of the function a to the x is itself times the natural log of the base. Or if this is a to a function u power, then we use the chain rule, and we'd have a derivative of a to the u is a to the u times natural log of a times du dx. So let's see it in action. At what point on the graph of the function y equals 2 to the power of t does the tangent line have a slope of 21? All right, so when we talk tangent line in any calculus question, we're thinking derivative first. So the first thing we want to do is differentiate with respect to the independent variable. So I'm looking for dy dt. So dy dt, first, we want to differentiate 2 to the power of t, and that's going to be itself 2 to the t times the natural log of the base. So times the natural log of 2, and then the derivative of -3 is 0, so we are done with dy dt. We would like for that dy dt, tangent line slope, to be equal to 21. So we can say equals 21 here and begin to solve. Now, we could use the calculator solve function and figure out an approximation for t, but just for practice, let's try to do this a little bit with logarithm properties and solve for t algebraically. I think the first step we want to do then to solve for t is divide both sides by the natural log of 2, and we'll do that here. Divide by natural log of 2, and now we have 2 to the t equals 21 over the natural log of 2. Next, we want to take t out of the exponent and move it back down to the line. So what the process of that involves is taking a natural log of both sides of that equation, and that uses natural log properties to take that t now from the exponent back out front as a scalar multiplier. So now we have t times the natural log of 2 equals the natural log, and we can use properties here as well, of 21 minus the natural log of 2. The natural log of a quotient is the same as the difference of the two natural logs. And then we continue to solve for t and divide both sides by the natural log of 2 divided by the natural log of 2. And there we have an approximation for t. Actually, I was missing a natural log in here, so let's put that back in. This is natural log of 2. So this will be the natural log of the natural log of 2. There we go. And now we have t is equal to the natural log of 21 minus the natural log of the natural log of 2. And that's all over the natural log of 2. In a calculator, this will be approximately equal to 4.921. And then what we'd want to do is plug that number back into the original equation. So y of 4.921 will be 2 to the power of 4.921 minus 3. And this is approximately equal to 27.297, and altogether now we have a point of 4.921 comma 27.297, and this is the place on the graph of the function y equals 2 to the t minus 3 where the tangent line has a slope of 21. All right, let's try exercise 29 before we finish this video. Here it is, a copy paste from the textbook. At what point on the graph of y equals 3 to the x plus 1 is the tangent line parallel to the line y equals 5x minus 1? So the first thing we might notice is any line parallel to this line is going to have a slope of 5. The next thing we want to do is look at the tangent slope to this function, y equals 3 to the x plus 1. So we want to find dy dx there. So dy dx is going to be a derivative of 3 to the x, which will be itself times the natural log of the base. And then the derivative of 1 is 0. We're going to take this and set it equal to the slope 5. And then we'll go through our properties of logarithms to solve for x. So step 1, divide both sides by natural log of 3. Divide by natural log of 3. Next up, that says 3 to the x is equal to 5 over the natural log of 3. Next, we're going to take the natural log of both sides to get x out of the exponent. Natural log of both sides. This leads us to an x times a natural log of 3 equals a natural log of 5 minus a natural log of a natural log of 3. Last, we'll divide both sides by the natural log of 3 divided by the natural log of 3. And that tells us then we have an x value of the natural log of 5 minus the natural log of the natural log of 3. And this is all over the natural log of 3. So we're probably going to want a decimal approximation of this, and we're going to use a calculator to get that. Natural log of 5 minus natural log of 3. So let's go to the calculator here. Let's set up a fraction. And we want the natural log of 5 minus the natural log of the natural log of 3. And this is over a natural log of 3. And that's going to be about 1.379. So let's get that down here, about 1.379, rounded to 3 decimal places. Last, let's get the y value. So y of 1.379 will be 5 times 1.379. Oh, that's the wrong function. Let's try that again. we want to do 3 to the power of 1.379 plus a 1. So let's try that. Back to the calculator. We're going to do 3 to the power of 1.379 and then arrow over back to the line plus a 1. And we have a y value of about 5.549. Let's get that. This is about 5.549. And so we have our point on the graph. It's 1.379, comma, 5.549. And that is derivatives of a base a to the power of x.